Hello, everybody. This is a weekly TCS seminar at Jagiellonian University. And this week we have Jędrzej playing for the home team, and hopefully we can enjoy his new results on weak coloring numbers.
Thank you very much. So the results that I will talk about, they are joint work with my PhD advisor, Piotr Micek, and my French colleagues, Juan Cla and Clément Rambaud. And as the title says, it's about weak coloring numbers. Let me start with something very simple, a coloring number of a graph. Let me recall the definition. We are minimizing over all linear orderings of vertices of our given graph. The following value, so the value that we're checking for every vertex of this graph, and we're counting number of backward neighbors of U in this ordering, in this linear ordering. And the thing that we obtain is called coloring number. It has many applications, especially in graph coloring. Weak coloring numbers are a generalization of this concept of coloring number. And I presented this definition first because the definition of weak, this definition is very well known. And the definition of weak coloring numbers is kind of a generalization of this. We'll see it in a moment. So weak coloring numbers, this is a family of parameters, and this family is parameterized by some positive integers. Usually they are called R. So I defined R weak coloring numbers, and the definition, as I said, is analogous. It obeys the same framework, but now we are maximizing over some strange set that I will define now. So it's a number of elements in a set W reach R, and W reach, these are vertices that are weakly are reachable from U, and we say that a vertex V, this pink vertex, is weakly are reachable from U if there is a path. This is a UV path, so it goes from U to V, and it has to satisfy some conditions. The first condition plays with this parameter R, so this path has only at most R edges. And the second condition probably has something to do with this weakly and coloring number. So here we enforce this path to has as a minimum vertex V. So we can only use vertices that are right to this vertex that we are reaching. And this is some example of a vertex that is weakly R reachable from U for R or 6 or something. So this is the definition. Now maybe some very simple things about this definition. If we take R to be equal to 1, then this is exactly the same definition as before. We exactly obtain coloring number, because now we are allowed only to use one edge, and it has to go backward, because the minimum of this new path has to be the endpoint, the last vertex of this path, the one that we reach. If we make R bigger and bigger, then this parameter will grow, because we always can reach more and more vertices. Maybe the same, but not less. Yes, so if I allow 2 edges, then I can reach more, probably, in most cases. So the next parameter, W equal 2 of G, is not less. And we can, of course, go on, and for all positive integers, we'll get the sequence of inequalities. We can even take R to be infinity. So now there is no bound on the length of this path. It can have arbitrary many edges. And it turns out that this W equal infinity of G is exactly the same as tree depth, which is probably a little bit better known parameter. Okay, so now let me this is a definition. It maybe doesn't sound very natural, doesn't look very natural, but let me try to convince you that this parameter is really interesting. It is natural. So first reason why we can believe that it's interesting is exactly the sequence of inequalities that I showed you before, because this shows that we are kind of finding steps in between two very well-known and very well-studied parameters. And sometimes it makes sense to try to understand intermediate steps between two well-known parameters. So this is what weak coloring numbers do. Next reason, which is probably the most prominent one, is that weak coloring numbers capture important notions of sparsity. For example, one can characterize classes of bounded expansion with weak coloring numbers, which is also very useful. We'll see it in a moment. Next, there are a few applications where we simply bound some value. For example, here, chromatic number of exact distance graph by some expression, which is just some weak coloring number of some graph. Also in posset dimension, we have a nice application of this. And finally, there is a lot of algorithmic applications. And what do we mean by algorithmic application? Is that we design some algorithms, and then we can bound time complexity of these algorithms using weak coloring numbers. And sometimes also during the algorithm, we have to compute some weak coloring number, but roughly weak coloring numbers, they bound time complexity of these algorithms. So this motivates the study of some nice upper bounds on weak coloring numbers. And this is what we do in this project. So we study, to be more precise, we study upper bounds on weak coloring numbers of graphs in some fixed minor closed graph classes. But before we proceed with this, I will try to give you some simple examples to maybe give some more intuition on this parameter, some more introduction. So let's do this for paths. Let's try to compute weak coloring number, not compute, but upper bound weak coloring numbers of paths. We will show this inequality. So arc weak coloring numbers of a path P is 2 plus ceiling of log R. And here I think it's not visible. Yeah. So we'll do this for R equal to 7. I mean, okay, we'll do this in general, but the example that I will present in a moment, I mean, there will be some picture, and on this picture, we will have R equal to 7. The ceiling of log R is now 3, and we'll show that the bound is 5. So we're taking a path. Say that this path has 22 vertices, and we're numbering them from 0 to 22. And now to each vertex on this path, we will assign one of 4 colors. And in general, this is one of 1 plus ceiling of log R colors. And let me show you how do we do this. So we start from the highest color, and highest color in this case is 3 because it's the ceiling of log R. And we assign 3 to every 8th vertex. So 0, 8, 16, every vertex of this form. And the important thing is that the distance between two vertices with this color is large, so it's at least R. Yeah, because okay, 8. Where does 8 come from? This is 2 to the power of 3. Yeah. So we okay, this should be clear. And now we will be constructing. So while prescribing colors to vertices, we will be constructing this ordering that should witness that weak coloring number is indeed bounded by this logarithm plus 2. And how do we do this? We take vertices with color 3 at the beginning. So the P0 is first, then P8, then P16. And I will draw them in a strange way, but at the very end, we will see why do I draw them in a strange way. We should see them for now as going from left to right. So P0 is the smallest, then we have P8, P16, and the vertical will be clear in a moment. Why do we care about this? Then we take every 4th vertex that is not yet colored, we put 2, and again we put them in a similar manner in order, like this. Then we do the same with color 1, we put them, and the remaining ones are color 0, and we again put them in order. And now this is the ordering. Why did I draw this like this? Because if I want to restore original edges of the path, they look like this. Yes, these are original edges of the path. They are this zigzag. Now, the structure that we get here has some kind of a tree structure. I mean, it looks kind of like a tree. Maybe it's not very clear what does it mean. Let's make it clear. So this, yeah, it should be visible, I hope. This green edges, we'll call them tree edges. They are not necessarily edges in the path. They are this is some meta tree, yeah? And it's kind of clear how do we construct it. We start with this vertex is colored with 3 as roots, and then we go down and we connect to the closest possible vertices in the next level. So it's a meta tree. It has depth 3, meaning that there are 3 edges from root to leaf. So we call the vertices of color 3 roots. And the claim that will end the proof is that we can weakly reach only ancestors in the tree. Meaning that, okay, so why is it enough? Because now if we have a vertex, meta trees of depth 3, so we can reach only 4, only in 4 levels. Maybe there are 2 roots. On each level, we can reach only 1 guy, but maybe there are 2 roots, because this is a strange tree with many roots, not just 1 root. So we can reach 1 in each level, but maybe 2 roots. Okay, so it's 2 plus 3, yes? 1 plus 3 is 1 plus log r ceiling, which is the depth of this tree, and then plus 1 for this additional root that we can reach. Okay, so let's verify this claim. Yes, that we can only reach our ancestors. So take some vertex, let's say this one. For other ones, the verification is similar, but we should focus our attention on something. And this is reminder of what did it mean to weakly reach something. There was a path with minimum with minimum exactly in the vertex that we are reaching, and this path was not very long. So what can we reach from this blue highlighted vertex? We can reach its neighbors, because its neighbors are more to the left, and it's 1 edge, so we can reach them. Yeah, the pink vertices here. And they are indeed, okay, here I highlighted how do we reach them, and they are indeed ancestors of this guy in the tree. Maybe I should say at some point that we can always reach ourselves. A vertex 1 reaches or 0 reaches itself. So this is yeah. Okay. Just a side note. What can we 2 reach? So the answer is nothing, because if we make 2 steps, for example, if we go through this edge and then this one, then we arrive to a vertex that is more to the right than this one. So we don't 2 reach him, because we kind of went back. So we 2 reach nothing. Next thing we can study is what we can 3 reach. And if you look at this picture long enough, you'll see that we can weakly 3 reach only this one, the new pink one, because 3 steps in the other direction, 1, 2, 3, we arrive here, but this one is more to the right than this one. So we don't weakly 3 reach. And the new vertex is again an ancestor, so it works. And I claim that it's 1 more, because we can go down and we can weakly 5 reach this vertex, and you can check that if we go up, then we don't 5 reach anything. And it's again an ancestor, so this is the second additional root. But now, if we want to go somewhere else, we have these blockers. We have this one and this one. They are kind of blocking the way up and blocking the way down. So the only candidate to be reached is now in color 3, because we cannot reach something with smaller color, because we always have to go through this one, and now it doesn't work. So maybe this one, but this is too far now. We have only r steps. So if we try to go to this one, it's too far. It's more than r. So this is okay. This was not maybe very formal, but it should give some intuition why this coloring works and why weak coloring numbers of paths are logarithmic in R. Yes. The important thing is that they don't, so this value doesn't depend on the length of a path. Path can be arbitrarily long, but it only depends on R. Okay. Questions maybe? Yeah. Okay. So we can go on. Maybe it's not obvious why the next step is with coloring numbers of graphs of bounded treewidth, but it will be clear later, much later. So what do we know about weak coloring numbers of graphs of bounded treewidth? We know a lot. If we have a graph of treewidth T, then there is a very nice bound of weak coloring numbers, R weak coloring number of a graph G. It's R plus T choose T. And what is nice, super nice about this bound is that it's tight. So there is an example show GRT, which we should remember because I will use this example, this construction many times. I will also show it in a moment, but the name for now we can just remember with treewidth T, such that we attain this bound. Okay. So I will try to show you, at least sketch you both things, so upper bound and the construction. Let's start with the upper bound. And let's first take a tree decomposition of G, optimal one with bags of size at most T plus 1. What do? We add all possible edges in bags. So this way we can obtain a chordal graph. This is some very simple exercise to see that if we add all edges in bags, then it's a chordal graph. We call it G prime. And we note that this chordal graph, it has still treewidth the same because the same tree decomposition works. So in particular, clique number of G prime is T plus 1. Chordal graphs, they admit perfect elimination orderings. I will tell you what is perfect elimination ordering. I will not tell you why chordal graphs admit these orderings, but this is also a very nice exercise and something not that hard. I mean, it's not very deep. It's quite simple. So what is a perfect elimination ordering? It's an ordering, again, ordering on vertices of a graph, such that for every vertex of this graph, the set of backward neighbors, so again, this we already encountered, induces a clique in G prime. Yes. So any vertex I take, I look back, and this is a clique. Yeah. Okay. This clique has this quantitative property. It has at most T vertices, at most T ping vertices. In this case that we're considering, because with U we form a clique, and we show that clique number is bounded by T plus 1. This is important. So I hope that this definition is clear. Now we go back to the proof of this upper bound. The proof is induction on R plus T. I will skip the base cases. They are simple. And actually, this is the ordering that we're taking. So there's this perfect elimination or ordering sum of this chordal graph that we obtain by this simple modification is the ordering that we're taking to bound weak coloring number. And so let's convince ourselves that it works. We're trying to bound the number of weakly R reachable elements from U in G prime in this order. So there is U. How do we bound them? Let V be this vertex in the neighborhood of U that is leftmost. First way of R reaching something from U is going through V. So one step to V, and then R minus 1 steps to the left. Yes, but here we can call induction on this graph from V to the left. To take V to the left, we need only R minus 1 steps. So the progress now is made here. We call induction, we get this value. And now we're only missing weakly R reachable vertices in this chunk in between U and V. So let's forget about everything we know about this chunk, and let's say that this graph from U to vertex 1 before V is called something like GT minus 1. And the important thing about this graph is that this property with perfect elimination ordering and having t vertices to the left, now this is t minus 1. Because this vertex v is kind of is almost universal vertex for this graph gt minus 1. Yes, because, for example, if you have this vertex here, and he has some neighbors, he always has also v as a neighbor. So in this smaller graph, he can only have t minus 1 neighbors because v is one of them. And we can continue. Yeah? It's here I'm not very precise, but it's not that hard to check that really we progress on this parameter t, whatever this is now. And we can add this value. Now we still need r steps, but we decreased t. So by induction, we get these bounds. And r minus 1 plus t choose t plus r plus t minus 1 choose t minus 1. This is r plus t choose t. Okay. So this ends the proof of the upper bound. And now we proceed with this construction, so lower bound. We can start however we want. Let's say that we start with an independent set with some number of vertices. This doesn't really matter. We can also start with one, but if we start with more, then some technical stuff works better later. And this is a recursive construction, I should say. When we construct GRT, we take gr minus 1t, and for every vertex, we attach a lot of copies of grt minus 1. A lot, I can specify later, but if you take some big function in R and T, it should be fine. And how do we attach them? We put all possible connections. So this green vertex is universal for the yellow stuff. And we do this for every vertex, as I said. So the new graph is very, very big. They grow very fast, but this is the construction. And we claim that our food coloring number is at least r plus t choose t. Okay, we also should justify why treewidth is exactly t, but this I will not do, but it's not hard. It's really not hard. So how do we prove this lower bound here? Say that we have some ordering of the vertices, and we want to show that there is a vertex that weakly R reaches a lot of stuff. So the green stuff and yellow stuff is somewhere in this ordering. So green stuff is somewhere. So by induction, there is a vertex u that reaches a lot by induction. So r minus 1 plus t choose t. And let's say this one. It's this one. It's u. U is somewhere in this ordering. Maybe I drew arrows. Maybe it was not the most fortunate. They don't have to be in connected parts of the ordering. They're somewhere spreaded, maybe. But U is somewhere. And now there is a small argument to show that it's not possible that for every yellow component under U, there is a vertex that is to the left of U. Because if this was true, so if for every yellow component there was a vertex to the left of U, then U reaches all of these vertices. So already weak coloring number is high. So this means that there is one yellow component that is completely to the right of U. Yeah, the situation, the opposite situation is quite okay, simple to understand. So let me go on. There is a component that is completely to the right of U, and we can call induction on this component. There is some vertex V that reaches a lot in this yellow component. But now, from vertex V to vertex U is very close. It's just one step. So this was r minus 1, sorry, here was in U was r minus 1. From V to U is 1, so altogether it's 1. So we have this lower bound of what we can weakly R reach from V in the whole graph GRT. This is this value plus this value. And if you add two such values again, we obtain binomial. So in some sense, Maybe this is kind of a reverse engineering of this proof of the upper bound, maybe. It's not very hard. I skipped some details, but I believe everyone can fill them in if they want that. So this is all for now I wanted to say about graphs of bounded tree width. We should remember this GRT. I will state it in some places, and we should remember. Okay, one can remember, of course, the construction, but the most important is that they have treewidth T, and weak coloring number is high. Omega of R to the T, if one wants just asymptotics. So now we move on to the main topic. So weak coloring numbers of X minor free graphs. We fix some X, and we want to study G that is X minor free. What do we know? So first thing we know is that this value is polynomial in R, where degree depends on the number of vertices in X. So G can be very, very large, but still this value doesn't depend on the number of vertices in G. And actually, there is quite nice expression. What is the exponent of R? It's polynomial, very nice. Okay, but now maybe we want something more. Maybe we want a better bound depending on the structure on X of X. So the list of results that I will present to you in a moment is going in this direction. We want better bounds depending on the structure of X. If X is simpler, then maybe we can do something better. So, for example, we can replace number of vertices with the vertex cover number, and we obtain a bound like this. Next, after vertex cover, something natural to consider is tree depth. Here there is this G, which is some exponential function, so it's not that nice anymore, but it's still a qualitative improvement because there are graphs with constant tree depth and unbounded vertex cover. Yes, so there are some graphs for which this bound is better. It doesn't depend on this function G. And finally, so in the project that I'm referring currently, we managed to get rid of this function G. Now it's just tree depth of X minus 1, and there is this small log factor. Okay, but this motivates the following definition. F of X, okay, on the bottom here, I put a very formal statement, but maybe we should just look here. F of X is this exponent of R weak coloring, maximum possible exponent of R weak coloring number of X minor free graphs. Yes, and one can define this precisely. I did it here. What does it mean? This means that all of the results here, they can be restated in terms of this F of X parameter. The first result is that F of X is at most number of vertices minus 1. Yeah? This should make sense, I hope. And then all the other ones, same way. Also, this treewidth result that we've seen is a lower bound on F of X, this treewidth of X minus 1. Yes. And maybe a small note, this new one, this that we proved recently, it improves on the second one. It removes this +1, and it reproves the first one. Actually, if you look inside, then there is this log factor. But if you only care about like clean integer in the exponent, then it's reproving the first one. Okay. So these are some lower bounds and some upper bounds on F. But we can also ask how does F behave in general? If we can maybe describe F in some way, maybe tied to some parameter, this would be nice. Yes. So if F was functionally tied to some parameter, let's see what we can do. So this is a repetition of the previous slide. This is a repetition of the previous slide. We have this sequence of parameters, of very well-known and well-studied parameters: treewidth, pathwidth, tree depth, vertex cover, and number of vertices. And we have F, which is at most tree depth in some sense, and at least treewidth. Yes, I'm ignoring this plus minus 1 terms. I'm only looking for this qualitative quality. Okay, and there is path width in between. So one can ask if f is connected in any way to path width. And the answer is no. Let me give you a small arguments why. So first, let's see why path width is not under f in this diagram. Consider a binary tree. If G is tk minor 3, then path width is bounded by some constant depending on t. This is classical theorem. We also know what this constant is, but let's not worry about it. Now, if okay, this is something that I won't show you, but it's not very difficult. When we have bounded path width, then it's quite easy to bound with coloring numbers, and we have some constant times r. This means that f of tk is at most 1 if you parse definitions correctly. So we're looking at tk minor 3 graphs and exponent in r in the bound of with coloring numbers. It's 1 here. Yes, this one here is this one here. But path width of tk is k. Yes. So we don't have we found a graph with large path width but small f of k. So this arrow is not true. Let's see the other one. We take a ladder with k ranks, and now if you look carefully, okay, this is again something to check. But if you take t to be very large and you take this GRT construction, or maybe I misspoke, to be not very large, and you take this GRT construction, then it's LK minus 3. But weak coloring number of such a thing is large. So f of LK is large, and path width of a ladder is at most 2. This is not hard to check. Yes. So again, we have two very simple constructions, just tree, just ladder, to show that path width is not good in any way. Yes. Also, this shows that tree width is not an upper bound. No, sorry. Am I correct? Yes, that tree width is not an upper bound, because if tree width was upper bound, then path width was upper bound, and tree depth is not lower bound, because if tree depth was lower bound, then path width was lower bound. So none of the parameters here is the correct parameter to consider for f. F is not tied to any of them. So what to f is tied? We had only one candidate that we didn't know that doesn't work and make any sense. And it's a parameter to tree depth, which I will define later. And it also behaves in the same way, in a similar way to path width, that it's an upper bound of tree width and lower bound of tree depth is not connected to path width at all. So this is first evidence that maybe it's worth considering. And actually it turned out that this is the correct one. And also we have one technical parameter which is called rooted to tree depth, and it's also tied to the two other ones. And I will define all of them and show you a sketch of a proof why they are tied. Okay, so the definitions of the key parameters. Let me start with tree depth, because just to be on the same page, just to go through the same definition. It's a recursive definition, so we're defining tree depth of x with some cases, and the cases are the following. And the intuition on tree depth is that we are playing a game on a graph, and we want to disconnect it as much as possible. So a graph may have some components. We're playing the game in parallel on components, but when we are given a graph that is really connected, we have to remove some vertex to disconnect it as much as possible, but we pay +1. And we want to minimize this value. Yeah. So this is tree depth. Is I'm sure It's quite well known and well studied. And one can try to modify this definition slightly to obtain two-tree depth. And the modification is that instead of connectivity, we care now about two connectivity. So whenever our graph is two connected, we have to remove a vertex. Sorry. We have to remove a vertex and we have to pay one to disconnect it again. But whenever it has some blocks, we play this game in parallel on all the blocks. Yes, one can go further and define tree depth k and so on. But here we only need two-tree. Now rooted two-tree depth is a technical variant of two-tree depth. It behaves the same, but when the graph is connected but not too connected, we do something more technical. Maybe let me sketch what exactly do we do. We're minimizing over separations of this graph, but these separations are very particular. So they are of order 1, so only cut vertices. So really, it's simpler than it looks like. We are choosing cut vertex, then we're dividing what's left into parts, and we're minimizing, and the parts have to be non-trivial, and we're minimizing such a value. So as I said, it's a little bit technical. I can show you an example also, but it's also not very important to us today. So if we have some graph, then as I said, we're choosing some cut vertex, then we're dividing the remainder of the graph into parts, and maybe we divide them like this. And we call this recursive definition on parts with this cut vertex, and here we don't add +1, but just call the definition. And on the other part, we don't take cut vertex, but we have to pay +1. So it's something in a similar flavor. But as it turns out, this technical statement allows us to understand the situation much better. Okay, so I defined two-tree depth and rooted two-tree depth. Now let me maybe give you some properties of the two parameters. Two-tree depth is quite new. It was recently introduced in some other context. As I mentioned on the slide where I was looking for a parameter to tie to f, two-tree depth and rooted two-tree depth, they are tied together, and this is quite tight relation by a linear function with multiplicative factor 2. And actually, this set of inequalities is tight. Here is an idea how to proceed with a construction that the second inequality here is tight. Also, it's a small example where one of the parameter is smaller than the other, which might not be obvious at the first glance that it can be done. Yeah, so this you iterate in some way, and you get a construction for tightness of the second inequality. Now, a nice thing is that, okay, so the first inequality is here, if you look at the definitions, is obvious. Second one is also quite easy, but the second one is important because we are working with this rooted two-tree depth, so we obtain finally some result with rooted two-tree depth, but then we can easily apply it to tree depth. So this is how we obtain this result when we remove this function g, this exponential. What else? Bounded tree depth is the same as excluding a path as a minor. And bounded two-tree depth is the same as excluding a ladder as a minor. This is very nice. Also, I think that if we have bounded tree depth k, then one of my co-authors worked on characterization what we exclude then, and I think there are some successes there. But maybe some other time we'll talk about this. Next, as I hinted, rooted two-tree depth is, okay, maybe I didn't hint this, but rooted two-tree depth is connected to this construction GRT very closely in this way. So intuitively, if we have a graph X, then it's the most like some GRT, and this T is exactly rooted two-tree depth. is the most similar to some GRT, and we're taking this T. Yes, and here is a formal statement on the slide. And why is it interesting? Because if we take now GR rooted to 3def of x minus 2, so here are some plus ones, and this is why we have to subtract 2, but let's skip these technical details. Then it's x minus 3. And it doesn't depend on x at all, only on rooted to 3def of x. So here we have a structural parameter of x, which tells us which GRT I have to choose, and then it's x minus 3. This is very nice. But now recall this. So this is the inequality that I highlighted before. If we plug this GR rooted to 3def of x minus 2, then we get omega of rooted to 3def of x minus 2 again. And what does this mean? This means that we just obtained a lower bound for f of x, because we found a graph that is x minus 3, but that has a large weak coloring number. So half job is done, because we have a lower bound. So now the only task is to prove the upper bound, which is of course much harder. But this hints that maybe this parameter is good indeed. So the main theorem, yes. What did we really prove? We have two theorems, one probably more important than the other, but I want to present both. GSX minor 3, and the first one is what more or less I already stated, that we have an upper bound where the exponent on R is something dependent on rooted to 3def of x minus 1, and there is this log factor. Yes? And here in the other theorem, we're trading 1R for treewidth of the host graph. So if host graph has bounded treewidth, then we can get something slightly better. Let's maybe phrase it in this language of F because it's simpler. So the first theorem, so lower bound was on the previous slide, and the upper bound comes from theorem 1. We are off only by 1, which is very nice, but was not expected at all when we started, because really we wanted just to find the parameter that is tied to F. And so we didn't really care what function we get, but as a nice bonus, we get a function, very good function. It's just off by 1. Also, maybe this 2-3def is something more natural and more understood. So we also obtain bounds with, that F is tied to rooted to 2-3def, classical 2-3def. From theorem 1, we can deduce equality even, because so if x is planar, then treewidth of G is bounded by some absolute constant depending on x. So treewidth of G, we forget about it, and we get exactly what's going on. So we get exact formula for f of x. That looks very nice. Some comments. The fact that we tied rooted to 3def with f, and also having in mind that rooted to 3def is very strongly related to this GRT construction, we can put some meta statement like this, that GRT is a universal abstraction for W codes, whatever this means. But it sounds nice. Next, I already mentioned this 3def of x result. So it follows from rooted to 3def, because as I said, rooted to 3def is less or equal than 3def, and we have this chain of inequalities. And finally, in this discussion, I want to mention the planar case, but not x planar, but G planar. Yes. So if G is planar, then we know that there is a cubic bound. There is also a lower bound R squared log R, and this lower bound has this nice property that the construction have bounded treewidth by some absolute constant. I think it's 3 or 4. So it's really bounded treewidth. And from what we prove from theorem 2, if you take as x k33, you obtain an upper bound. Only in this case of planar with bounded treewidth, which is tied with the lower bound. So this is nice. Of course, it doesn't solve the general problem. It's still open. What's the order of magnitude of W core R of G in the planar case? And we believe that actually it's closer to this value, not to this value. But this is still open, as I said. We only have result for planar graphs of bounded tree. Okay, so before I start to describing our proofs, I want to give you a short overview of something called chordal partitions technique, which also is one of the building blocks of our proofs. And what I will show you is this first result that I stated on a slide with x minor 3 graphs. So if G is x minor 3, then weak coloring numbers are bounded by some function with a number of vertices in the exponent. And let's maybe keep things simple. Instead of x, now we can just consider kt. Yes, because we only care about number of vertices, so we consider kt minus 3. And the bound should be now r to the power of t minus 1. So a geodesic in a graph is the shortest path between two vertices and the shortest path between two vertices. What is nice about geodesics and weak coloring numbers? If we have a path that is a geodesic and we study this reachability set of G sigma u, and we only care about the vertices in this path, then then there cannot be a lot of them. Let me show you why. Say that we have P, which is geodesic, a geodesic, and we have our vertex U, and say that U reaches some stuff on this path. And say that it reaches a lot, so more than the bound that we want, 2r plus 1. This means that the number of edges here between the first that is reached and the last that is reached, it's at least more than 2r. Yes, this is very simple. Okay, but if here you have more than r, but u reaches stuff, so it's less or equal to r, then there is a shortcut. It's better to take this black path above than to go through the path, right? Because the shortcut has at most 2r vertices, and on the bottom you have more than. And this observation is more general than for weak coloring numbers, but because here we didn't use at all this structure of this path in the ordering, but also it works for every sigma. This is already suspicious. So, but this is because it's more general. But here I wanted just to show you this application. Yeah. So because there would be shortcut, we cannot reach too many vertices. Now this is just a reminder of this result about treewidth that I showed you, but stated in slightly different way. If we have perfect elimination ordering of width t, and by width of perfect elimination ordering I mean this value here, then we have this bound on weak coloring number. Yeah, this is just reminder of what we already did. And what's the goal now? We cannot apply this result to our graph itself because it maybe doesn't have bounded treewidth. Yes, it can have arbitrary treewidth. So the goal is to partition a graph into pieces, and pieces should be such that they admit perfect elimination ordering with of width something bounded in terms of t, and each piece is connected, and each piece is the union of some small number of geodesics. Here I'm cheating a little. It's not. I didn't say where these geodesics are. Maybe they are in smaller graphs, but this is quite technical, so let me not dwell into this. But let me visualize the goal. So visualize what we want to do. So instead of vertices in this perfect elimination ordering, we put some pieces, I don't know, subgraph. Still, we want to have this property about reaching stuff. Now instead of t, it should be t minus 2. And each of the piece of the pieces is just union of some small number of geodesics. Maybe let me comment on this t-2. This is for free, actually, because if you have pink pieces and blue piece, they for a minor. They for a minor of a click, because I insisted on connectivity of the pieces. So you cannot have t. So t-2 is for free. If you have a perfect elimination ordering, then it has of this kind. Then it has at most t-2, this width or whatever. So why it's enough? Say that we take this ordering on vertices of the graph, and inside of the pieces, I think we can do whatever we like. It can be arbitrary. And we want to show that with this ordering, that I described, this W-rich set is bounded. So why? When I'm somewhere, by this argument that we discussed on bounded treewidth, I can reach only this number of pieces, of other pieces. In each piece, I have at most t-3 geodesics. In each geodesic, I can reach only 2r+1 things. So if you write this as r to some power, it's r to the power of t-2. Here you have one more. This is just some multiplicative constant. So you have O of r to t-1. And this is what we wanted. So now the only thing that remains is to achieve the goal. So find this partition. How do we find this partition? This is just a restatement what the goal is. It's an iterative construction. There is some invariant. Invariant says that, okay, maybe I should start with a picture. Say that we already constructed some pieces, and there are some remaining components. And the invariant says that if you fix a component, if you choose one, let's say that I chose the big one, then neighboring pieces form a clique. This is what invariant says, and I'm using it here. Yes, I chose some arbitrary component of the remaining stuff. I know that what it neighbors is a clique, and yeah. We also know that it's at most t-2, which is not that important. Now, for every component that we're neighboring, we're choosing some vertex with a path to this with an edge actually to this component. Maybe for some components we chose the same vertex as here. Yes, so I'm just choosing some representatives. Now I'm connecting the blue vertices with geodesics in an arbitrary way, but they have to be geodesics in the remainder of the graph. Here is this place that I cheated, but it's fine if you check it carefully. So these are geodesics in this part, actually in this component. You cannot use the other components. Okay. So since here you have only t-2, you only need t-3 geodesics to connect them, because you connect first to the second, then maybe first to the third, and so on, and this way it's connected. And now you do a very simple thing. You just take the geodesics that you constructed, and you make a new piece out of them. Yeah. Now, what happened? The new piece with the pink pieces, they form a clique. So we have to check the invariant. Of course, it holds for the old components, for these ones, because nothing changed. So let's see if it holds for the new components here. It holds because they can only be connected to something either pink or green, because the vertices in the new components created here, they were connected only to the pink stuff. Yes, this was the definition of pink stuff, actually. So it's connected to some subset, but subset is also a clique. It's fine. So invariant holds. Now, yeah. So this is the end of the proof. Yes, because we achieved the goal. We found this partition, and on the previous slide we showed how to wrap it up and find the partition. Yes. So in some sense, we get a graph and we want to find this partition of vertices. Yeah, okay, maybe I should stop here and just go on. So now a glance at the general proof. So I will only talk about theorem 1. Theorem 2 is some technical modification, which a lot of big chunks of the proof overlap, but not everything. It's more technical, so let me not talk about it. Just theorem 1. So this is a pretty theorem. Let me state a technical version of this theorem, which is induction claim. Yes. So we have two parameters, t and k. Now we assume that G is kk minor 3. I will explain it later. We take any family of connected subgraphs of G. This is new. We say that G has no F-rich model of G QT. Q, I will not specify, it should be something, but F-rich is the important part. I will explain it later. In particular, it has no model of GQT. And okay, maybe I should comment at this point that I don't consider X, I just consider GQT because of the definition of, not definition, but the property of rooted to tree depth, that it was similar to being, to how similar X is to GQT. So, and I change R to Q because R in this place can create some confusion with R in the enumerator of weak coloring numbers. Okay, so this is a lot of details, maybe unnecessary, and these are assumptions. The assertion is that there is a vertex. There is a vertex subset of vertices, such that first S hits F. What does this mean? It means that it intersects every member of F. This is technical stuff, but it's important that G of S is connected. And finally, we have something like this. And this I will explain also later in more detail. So this is some technical statement. And let me try to explain some parts of the statements one by one. How we should think about it, okay, maybe how we should see that it's similar to theorem 1, we should just look at the highlighted statement. So G has no model of something, then weak coloring numbers are bounded by something. Yes, this is how we should, this is why it's close to theorem 1. Let's maybe see why technical statement implies theorem 1. We take T to be rooted to tree depth of X minus 1. We take K to be in a number of vertices of X. So this is again purely technical, but when we are X minor 3, then for sure we are KK minor 3, where K is the number of vertices. So this is something weaker, but okay, I will talk about it later. And if we take F to be all one vertex graphs in G, then we are forced to take S to be all vertices because S has to hit F. And if we know the definition of W called RGS, we will know it in a moment, but now we don't know it, then we'll see that it's the same. So, okay, this is how to obtain theorem 1 from this technical step. Now, maybe let's move to something more interesting than just playing with notation, rich models. So I mentioned F-rich models of something. Let me just give you the definition first. If we have a family of connected subgraphs of G, then a model of something is F-rich if every branch set contains a member of F. Yes, so for every V in X, there is some subgraph in F that is contained in the branch set of V. So an example, this is just a model of C8. Yes? This is how I want to depict model. Some branch sets and they are connected by edges. Now this model is F-rich if every branch set contains a subgraph, some subgraph of F. And I depict the subgraphs by some orange stars. Okay, so this was an abstract example. Let me give some more specific example. Let's say that we have some vertex U, some underlined, just some chosen vertex U, and F is all connected subgraphs of G containing a neighbor of U. And what is an F-rich model now? And an F-rich model now looks like this. Every branch set has to connect to U. Yes. Now every branch set actually has to be a member of F. This family F can have a lot of graphs inside. But this is an important idea. Okay. If we look at this picture, we'll see that from an F-rich model of C8, we obtain just a model of K1 plus C8. So K1 plus meaning that we add a universal vertex, and U is this universal F vertex connected to everything. So what is the general idea behind the F-rich models? The general idea is that if we have a F-rich model of X, usually we want to craft F and X so that we can obtain F prime rich model of Y, where we started with a complex family and we go to some simpler family, slightly simpler family. And we start with a very simple graph and we build on this graph, we make it more complex. So for example, here, I started with family that was fairly complex and I obtained nothing here. It's nothing rich, but nothing rich also means that if you take all subgraphs, then it's this rich. So, and this is simpler family. Yes, and also we started with C8, but we obtained something more complex, more complicated, with more structure than C8. Yes, so this is a general idea behind introducing F-rich models and why they are very good in lifting induction statements. Because we start with something very, very complex, I mean this family F, and we go to something very simple, and we saw that in the final application, maybe let me skip to this, in the final application, we take F just all one vertex subgraph in H. So this is very simple. We go from complex to simple. Okay. Maybe this is enough about rich model, unless there are any questions. Okay. So let's go back to this thing. The thing is that no F-rich model can be a very local condition. For example, in the example that we consider, the stuff that we are interested in is close to U. So graph can be very large, but the condition is only local. This is why we need this additional assumption that may look stupid, that G is KK minor 3, because this is a global assumption on the whole graph. Yes, and this F-rich model, no F-rich model can be very local assumption. And also, because the assumption is local, we can only obtain some local statements. And here it's more complicated. What do we mean? But we only obtain a statement for the set S. It's here. I will explain this notation in a moment. But you see that it's dependent on S, so it should happen somehow close to S. And S is close to this family F. Yes, it has to hit it. It's connected, so it kind of connects this family F. But the intuition behind this technique, this whole technical statement, is that the thing that we're doing can be very local in a graph. Okay, so let me give you a definition of this localized variant of weak coloring numbers. We fix some subset of vertices S. And the definition is the same, but here there is some dependency on S. Sigma is now only linear order on S, so on this fixed set. And we're, for a given vertex U, it can be in S or not in S. In W reach of U can be only vertices in S. So we are checking reachability only to vertices in S. And the definition is the following. There is a path with the same properties as before. Yes. But now we only care about vertices in S. So this is why we say that it's kind of local, because we only measure, we only count number of vertices that we can reach in S. I think yes. I think it's only in it can. maybe I should. Okay. So I will not tell you more about this definition, but just to give some intuition why. What do I mean by local, which a word that I repeat a lot here. And finally, let me give you kind of a plan for this proof. It's by induction, of course, and okay, again, yeah. And the pre-base case is t equal to 0. When t equal to 0, then this GQT is an edgeless graph, so just some independent set. And one interesting thing about this case is that G has no f-rich model of GQT, so independent set, is the same as saying that there are no Q pairwise disjoint members of f in G. So this means that our technical statement is, in some sense, very generalized Helly property. But this is maybe quite far-fetched statement, but still, you can see some relations to this. In this pre-base case, we get linear bound. Now, base case is with t equal to 1. I will tell you why do we have to do both, why we have to do both. And in this case, GQT is a forest. So, okay, maybe let me tell you now. This is because if we didn't do this base case by hand, by hand, we would obtain from our induction R squared here. So this is how we save one in the exponent, and we trade it for with log, doing some more work. And here I put some comments why this is possible. So excluding a forest is the same as bounding path width. And if we do this argument for path width, but very much generalized, sorry, for paths and for path width actually, but generalize it very much to this statement, this technical statement, then we really can get O of R log R. No, and the induction step is this. Oh, it should be T at least 2 maybe. It's done in 2 steps because you can maybe recall the construction of GQT. There were some universal vertices attached to something smaller in induction. So this is why in the first step we're attaching universal vertex, and then we go up. And this thing that I show you with f-rich models is a very rough idea of why this step can work and why this induction statement with f-rich models is useful in proceeding in finalizing this step here. Okay. So this is all with coloring numbers. And I have one more slide just to wrap up this talk about p-centered colorings. So just, okay, maybe just a comment first. Weak coloring numbers and p-centered colorings, they usually come together in some places, various places. For example, they both characterize bounded expansion classes. And there is also a lot of applications of p-centered coloring, but I think they are not related in any direct way, at least not in a sense that from the results that I listed about X minor 3 graphs, we can derive on weak coloring numbers, we can derive anything from p-centered colorings. So this is why, I mean, it's appropriate to talk about them in this talk because they are really connected. Also in proof techniques, in terms of proof techniques, sometimes you can find some similarities. So the definition, these are colorings, and the coloring of a graph is p-centered if for every connected subgraph, either we use a lot of colors in this subgraph, so at more than p, or there is a color that is used uniquely in this subgraph. So this pink color here is it's called usually a center. Now you can define p-centered chromatic number of G. And as before, we care about p-centered chromatic number of X minor 3 graphs. So what is known? Filipchuk and Siebers, they proved that it's again polynomial, but this time not that nicely polynomial, because in weak coloring numbers, here, this first result that I listed was a number of vertices of x minus 1. And here we have some h, which is dependent on structural theorem of Robertson and Simon. So not very nice function. But we managed to improve it, and now it's the same as in weak coloring numbers. We also believe that we can do everything that I showed you for p-centered colorings. I mean the rooted to 3-depth stuff and everything else. This one is written down, so I listed it here. It's not yet public, but it should be soon. And that's all from me. Thank you.